with ICC World Cup on fire, there's a heated debate that's going on whether net run rate formula that is used in decision making regarding teams ranking, whether it is an appropriate formula or does it contain some anomalies and biases. So in this short video, we'll try to investigate mathematically what's going on and basically try to figure out any bias in this formula and any scope of manipulation in this particular formula. There have been claims that this formula adversely impacts the side which bats second, and especially when the opponent have scored very low scores, then the side batting second adversely gets impacted. So these are the claims. Let's see if they hold water. So this is the formula. So let's see it from the perspective of team B. So we are trying to calculate the net run rate of team B, and what the formula says is that the runs scored by team B divided by overs used by team B subtracted by runs scored by team A divided by overs used by team A is the net run rate. And as the tournament progresses, the calculation is done over multiple matches. Now the first observation that is very glaring is that this formula only talks about scores and overs. It doesn't talk about wickets at all. And there have been very fiery debates on this issue because there is no consideration to the wickets taken or wickets preserved, which is again reflective of a team's capability. But somehow this formula does not capture it. It does not treat wickets as a cricketing resource. So notwithstanding, let's go ahead and analyze this formula further. And the other rule related to this formula is that if any team loses all its wickets, then irrespective of how many number of overs that team has played, the team's counter will be maxed to 50 overs. So it will be assumed that the team has consumed the entire quota of 50 overs. So obviously, if a team gets bundled out for very, say they are playing very aggressively and they get bundled out in the 40th over, say, so it will be assumed that they have played 50 overs and their net run rate will be drastically curtailed. So the formula severely punishes the team which loses all the wickets. So these are the two general observations on this formula, and we are going to now consider some use cases, some scenarios, 4 of them, and see whether the claim regarding batting first and batting second makes any sense in this or not. So let's take case 1, where we will be doing this entire presentation from the perspective of team B, which is our team. So in this case 1, our team B bats second, and the scenario here is that the team wins. So under these circumstances, how the NRR will be calculated. So let's start with team A gets to bat first. So it scores X runs, and either it consumes all its overs, which in that case will become 50, or it gets it loses all its wickets. In that case also the number of overs consumed will be 50. So for team A, the side batting first, the number of overs consumed will always be 50. And the outcome of this match is that they have lost this particular match. Let's see how team B is going to win it. So if team A has scored X number of runs, team B needs to just score one more run to win this match. So the score of team B will be X plus 1 runs. And in doing so, it can consume Y number of overs. And Y can be anything from first over to 50th over. It can assume any value. So under these circumstances, because they have scored one more run additional, so they are going to win. And net run rate formula will be runs scored divided by overs used. So these are the runs scored divided by the over used by team B, minus runs scored by the opponent, which is X, divided by the overs consumed, which is 50. Now here one thing, and as I said that we need to put a constraint on Y, which is the overs. At least one over must be bowled to bowl out the other side. In fact, at least 10 balls must be bowled for the other side to lose all its wickets. And you cannot bowl more than 50 overs, which is the cricketing rule. So this particular conditional constraint catches that rule. The more interesting part here is that if you see this Y is appearing here in denominator, and anytime linear or non-linear variable, if it appears in denominator, it's a divide operation which is going on, and this makes this entire equation non-linear. And I'll talk more about it when we do a simulation on this. But just note that this Y is in the denominator, and then it results in a multiplication like this, which in statistics is called as interaction between the variables, which makes the equations non-linear. So let's move on to case 2. In case 2, again, team B, our team bats second, and this time, unfortunately, it loses. So let's play out this scenario. Again, team A is free to score X number of runs, and they will always consume 50 overs, either by way of consuming the entire quota of 50 overs or getting bowled out, the entire team getting bundled out. So their situation remains the same. And since now Team B has lost, so obviously it has scored lesser number of runs in comparison to Team A. And that lesser number of run is captured by this variable dx, which is the run deficit or run margin which Team B fell short of. And obviously either the entire team has got bowled out, or they have consumed the entire 50 overs and yet not able to reach the target that Team A set. So they will in all cases consume 50 overs, and this will result in a loss for Team B. So in this scenario, how does the NRR formula looks? So x minus dx are the runs scored by Team B, and the number of overs consumed is 50. And Team A has scored x runs, and they have also consumed 50 overs. Now you see something very interesting happens. Both the teams by default will have a denominator which is 50. And when we pull it out, what remains is this run margin, negative of run margin. So, and this negative run margin can be anything. Team B can lose the match at least by 1 run, or in the worst extreme case scenario, it has not been able to score any run. It has got bundled out on 0. So it cannot obviously then exceed the runs scored by the other teams. So this dx is a constraint variable. This one represents that the team has won at least by 1 run. The team B has lost by 1 run. And x means that the team has not been able to score any run. They just got bundled out for 0. So analysis here is that overs actually played by both the teams play no role, because in the denominator it will always be 50. And a point to be noted here is that NRR is directly proportional to the run deficit. And larger this deficit is, more adversely Team B's NRR is going to get impacted. Now let's take 2 more cases. In the first 2 cases, Team B batted second. Let's see when it bats first. So this is case 3, where Team B bats first, and in this case it wins. So Team B is here. Team B is free to score as many runs as it wants to, or as it is capable of, and in doing so it consumes all its overs, 50 overs, or they get bowled out. So this variable will always be constant at 50. And Team A fails to chase the target, and they fall short of dx runs. So dx is the run deficit. And in this case also, either they get totally bundled out, or they run out of their 50 over quota. So this will always remain 50. In this scenario, again, we calculate the NRR. So runs scored by B, X, overs consumed by B, 50. So here they are. And similarly, runs scored by Team A divided by overs consumed. So this is that variable. Now here, again, the same constraint remains. And what you'll see is that in this case, the NRR is directly proportional to the run deficit by which the Team B has won. Overs actually are playing no role. They are again constant at 50. So if Team B is batting first, and they are able to win with a big run margin, then their NRR is going to get boosted very strongly. Let's come to the last case. Now here the Team B again bats first, but unfortunately loses. So let's see the scenario here. Team B is free to score as many runs as it is capable of doing. So it scores X runs, and in doing so it exhausts its either overs or its wickets. So 50. And obviously Team A has scored 1 more run than Team B, and that's how they have won this match. So the run score will be X plus 1. And they can use Y number of overs, which can be anything between 1 over to 50 over to achieve this target. So here again, let's calculate the NRR formula for Team B. So X divided by 50, which is here, and X plus 1 divided by Y. And again, here you notice that Y is coming in denominator. And denominator, any variable which goes in denominator makes the equation non-linear. So this is, so we stop here as far as presentation is concerned, and my objective now is to go to Python and try to simulate all these parameters and see, visualize the anomalies and biases, if at all there are any. So we are here in Python environment. I've imported some libraries here, and so first of all I want to demonstrate that non-linearity that I was talking about. So what I intend doing is that I am going to generate an x-axis which is going from 1 to 10. I'm going to generate 100 points. It's linearly spaced, as you can see from this function. And then I'm going to generate a line with some slope and plot it against this x-axis. And then I'm going to take inverse of this 1 by y and plot that too. So if I run this code, what we see here is this is the x-axis going from 1 to 10, and we have 2 plots here, y and 1 by y. Y is in red color and 1 by y is in green color. So you can see y is a linear function. It is going as a straight line. But when we invert it, the 1 by y function, the division function, becomes a non-linear function. And this is exactly what is happening in the presentation that I showed you. This is what is happening. It is in denominator, and when you factorize this equation, when you solve this equation, you come across a term like this, which statisticians, they know it as interacting variable or interaction effect, which makes the system nonlinear. So we move on to our first case. I have declared some variables. The meaning of the variables remain the same as shown in the PowerPoint previously. And the case that I'm taking first is team B batting second and winning the game. So remember, there have been claims and counterclaims that team batting second is at disadvantage. So that's the reason we are doing this simulation. Rest everything remains the same. We are using the same formula for NRR. We are putting some constraints regarding number of overs, etc. And more interesting part is that I'm simulating runs scored by the first team A, and it is varying from a low scoring match, which is just about 100 runs, to a high scoring match. I wish to see the impact of score on NRR. So whatever the score team A achieves, does it have any impact on the NRR of team B? That's what is the objective of doing the simulation. And so I'm simulating all possibilities, starting from a low scoring match at 100 runs to going up to almost 400 runs in steps of 25. And this is achieved again through various combinations of overs, starting from 20 overs, going up to 50 overs in steps of 5. And for each of these combinations, I'm going to calculate the NRR and plot it. So let me just run this code. And so firstly, let's see whether we have captured the equation correctly. If you remember in the PowerPoint slide, our case 1 had this formula. So minus x divided by 50 plus x plus 1 divided by y. So that has been correctly captured here. The constraint is also, the y constraint is also captured correctly. That means a minimum of 1 over should be bold, and less than 50 over should be bold. So let's analyze these plots. So the first is this plot on the left side, which is called heat map. On the x-axis is over taken by team B to achieve to chase down the score, and on the y-axis we have runs scored by team A. So remember, this is by team A, and this is by team B. Team B only has control over how aggressively they want to play. They can play slow, they can play fast, and we just want to see the impact of it. And lastly, this color bar is basically showing NRR. So yellow or green color is very high NRR. This is for team B. As I mentioned earlier, also we are doing this entire analysis from the perspective of team B. So so the yellow and green colors, they are very high NRR, good for team B, and dark blue are poor NRRs. So one effect you can very clearly see if you see area above this curve. Area above this curve is more greenish and yellowish, and this part of the heat map is very dark blue, which indicates that something strange. I mean, the partitioning of this heat map is not in a linear fashion, and that is also very evident from this graph. If you see, again, this is a 3D graph, it's not a heat map. So in this graph we have runs scored by team A, which is the same axis here as heat map, and overs taken by team B, which is the x-axis. And now we are plotting this NRR on the third axis. So as you can see, these are not straight lines, these are curved lines, which obviously are a fallout of that divide by y factor, the denominator factor, and this entire function becomes non-linear. So how to go about interpreting it is in terms of the score. So let's say if we have very low scores, let's see the heat map first. So let's say we have very low score, 150, just about 125 or so. So irrespective of how many numbers of overs you play, the region remains very dark blue. Obviously, if you take a huge number of overs, if team B takes huge number of overs to achieve such a low score, their NRR is going to be very low, which is indicated by this dark blue. But even if they take very less number of overs, say for example 20 to chase down 100, 150, still it is quite bluish. And this definitely seems to suggest, because of the non-linearity in the system, that a low scoring match can impact the net run rate of team B in spite of team B winning it. This is very evident from this heat map, and again we can see it from here that this is a very low scoring match, and this is the overs axis, 20, 25, 30, 35, etc. But all throughout this entire region remains very blue. The green part or the yellowish part of the region is upwards of this, which means a a high scoring match, which means in which team A plays well and scores at least respectable score. And if team B is able to chase that down, their NRR is going to be much superior in comparison to a low score match. So that claim is clearly visible here. Let's take the second case. Again, we are batting second, and this time we are losing, and this is going to be the worst situation possible. So let me just, again, everything remains the same. Here, I am just simulating the run deficit or the run margin, where I'm saying that from one run margin to almost the entire score of team A, team B has not been able to make. So what is the impact of that? So firstly, if you, let's see if we have captured the equation correctly, it is minus dx by 50. And this is exactly what we had seen here in our PowerPoint with the similar same constraint. Obviously, team B can either lose by one run or by the entire score that team A has scored, or any run in between. So that constraint has been put in the system. Now, as you can see very clearly, firstly, the overs are playing no role. This is just a constant. And the entire net run rate is being controlled by the run deficit. It is a straight line, there's no non-linearity. In fact, for every 50 run deficit, the run rate drops by -1. So actually, if you can see from 1 to 50, and the run rate has dropped by -1. If we go to 100, the run rate will drop to -2, and so on and so forth. So this is quite drastic, because this is a very bad situation to be in. Firstly, you are losing the match, so you're losing the point. And if you're losing big, that means the run deficit is too high, your NRR is going to be very badly impacted. It's directly proportional, in fact. It is linearly increasing. Now, let's come to the case 3. Here, now we are seeing the opposite thing. Here, our team B bats first and wins. So again, we calculate the run deficit, which means now the team A has not been able to chase the score, and they can fail anywhere between from 1 run to 350 runs, and team B has scored 351. So let's see the impact. Here the exact opposite is happening. Firstly, the formula has been correctly captured here. This is this case, team B bats first and wins, and this is the formula. So if you see here, firstly, again, the overs, actual number of overs played are playing no role, it's a constant here. And secondly, if you are playing first, then the run deficit directly gets reflected into your NRR, and it's unbounded. You can, as you can see, this is rising continuously. So the more is the run deficit, the more runs by which the team A is losing, it directly gets reflected in the increase in your NRR. And same story here. If your run deficit or run gain is 50, then you increase your net run rate by 1. If you have a run deficit, if you defeat the other team by a gap of 100 runs, then your NRR is increased by 2, and so on and so forth. So this is a very good situation to be in, because firstly you have won, so you got a point, and your NRR is also increasing favorably. And let's see the last case. Now here team B is batting first, but unfortunately it loses. And let's see the impact of that. And again, I'm simulating a very low scoring match from 100 runs to 400 runs in steps of 25. And the over consumed is 20 to 50 in steps of 5. So this is the scenario. This is our case number 4, this case. And we have correctly captured the formula and the constraint here. And something very surprising is happening here. So remember, we have lost here. If you see the case, we have lost here. But is it possible that even after losing, your NRR is not so badly impacted? So let's see. Let's investigate that claim. Here, again, you see x-axis is overs taken by team A to chase down your score. And this is y-axis is the runs scored by team B. So obviously, team A has been successful in chasing the score. That's the reason why we have lost. But let's see the impact of low score versus high score. And here, actually, if you see the color code, yellowish or greenish color code means a very low impact on our NRR. These are very small values. Remember, they are all minus now. They're all going to get subtracted from team B's NRR. So a yellow indicates a very small amount which is getting subtracted from the NRR, and blue indicates a very large amount. So this is a bad situation to be in. But if you see this graph, this heat map, and because of this non-linearity that we saw in the system of equations, This bluish area is contained only in this region. And if you see below this, everything is green and yellow. So how to interpret it? So even if you are, losing on a low score, 150, 200, so as long as you have made sure that team A has consumed at least moderate number of overs, your NRR is not going to get impacted so badly. And that's because of this non-linearity in the system of equations, which is a good thing to have. So the claim that people are making is that batting second is disadvantageous, seem to have some weight. So let's just go back to our presentation. So let's summarize this entire situation. Let's see all our 4 scenarios. So in the first scenario, we batted second. Remember, the claim is that batting second is disadvantageous. So the first case is that we batted second and we lost. This is the worst case scenario. We are going to lose the point and our net run rate can drop very drastically. It is all dependent on how much of score that you could not make. That run difference is directly proportional to the net run rate. And the advice there is that don't lose by a big margin. If you are chasing, don't lose by a big margin, because both your points and your NRR is going to get very severely affected. The second case is batting second and winning. So at least you have won the point. Let's see the impact on net run rate. Here, what goes against you or team B is the low score. If team A has been bundled out for a very small total, which in fact is reflective of your good bowling, your bowlers have been able to bundle them out at a very low score, you might even be able to win the match. But as far as NRR is concerned, that can go against you, which is very contradictory. The NRR is moving in the opposite direction as against the number of points that you have scored from the match. So here is some manipulation that is possible. You can do loose bowling, you can do poor fielding, and make sure that the opponent scores larger number of runs. Obviously, here the assumption is that the point that you are going to win is not much of consequence and you are more focused on the NRR. The third case is we bat first and we win. It's the best case scenario. Here again, we have won the point, and as far as NRR is concerned, it is directly proportional to the run deficit, which means the bigger the victory, the larger the NRR. Every single thing will get reflected in your NRR. It's a linear function. So it's a very good situation to be in. Bat first and win. Get your point and improve your NRR significantly. The last case is not so bad case. Obviously, you have batted first and you've lost. So obviously, 1 point has gone. But how badly does it impact the NRR? So as we've seen in the simulations, if you have scored, high score, then your NRR will not hurt too much in spite of the fact that you have lost the match. And that's a very big finding. So this is, these are the, I would say, this is how the mathematics behind this formula is working. And not that teams are innocent. They know that this manipulation is possible. There are biases in the formula. So there are 2 ways in which the team can manipulate NRR in their favor or to eliminate somebody from the points table. First is scoring fast or scoring slow is in the hands of the team. For example, if I'm assured of a victory, I know that I'm definitely going to win this match. I can always slow down my score to not so badly impact the NRR of my opponent. And if my opponent is tied up with another team in the table on NRR, then my opponent has the benefit. He might qualify and the other guy might get dropped out. And this is exactly what happened in World Cup 1999. It was a match between Australia and West Indies. Australia had already qualified. They just needed to win this match. But New Zealand and West Indies, they were both tied on points, and NRR would decide their fate. So in this case, Australia pulled a smart one. They just slowed down their scoring rate so that West Indies' net run rate is not badly impacted. Though West Indies lost the match, but their NRR was better than New Zealand, and as a result, New Zealand got knocked out. So here is a live example of the pitfalls of this NRR formula. As I also told you that low score and high score also matters. So here again, there's a potential to manipulate the NRR. How you can do it as a bowling team is that you can bowl poor balls, or you can have a very sloppy fielding, just especially against a very poor side, like say a tailenders team like Netherlands or Bangladesh or somebody like that, where you are assured of the win, but you want your NRR to increase, and for that you need your opponent to score much higher score which otherwise they would have done. So you can resort to poor bowling, you can resort to poor fielding, so that these guys, they can score more runs, and as a result you score a bigger target and improve your NRR. So definitely there's a lot of scope for improvement. I will end my video here.